All right, this is day 2 of properties of planes, and it is the last day before we sort of move on to the second half of this unit where we're talking about or solving some other kinds of problems that involve lines and planes. The first half of this unit was really about getting used to the new notation and thinking about lines in 3-space and then thinking about planes. And a big part of it is the properties of planes, how they define the plane, how we can get those properties from equations, but then also use them, as we're going to continue to see today, to solve some problems around them and just think about them, visualize them, compare them to other planes, that sort of thing. And the second half of the unit is going to be a fair bit of that sort of similar stuff. Like all the stuff we're doing right now is definitely going to be important moving forward, where we have lines and planes and we're comparing them. We're thinking about them. How are they related? How are they similar, different, whatever. Okay, so keep that in mind that even though I'm saying first half, second half is always going to be related to the first half. Even though we are going to see a difference in the types of questions that were asked. And today is going to be a little bit different from yesterday as well. So I think we're doing about 4 questions here. And the first question is determine if each pair of planes, so I've got 2 planes, how do I know, whoops, that's not right. How do I know these are planes? Well, the pi out front, we talked about this before, but beyond that, I really do want to just look at the equation and be able to determine that this is a plane. And I can do that because it's 3-space, because I've got x, y, z, and a scalar equation in 3-space is a plane. It is not a line, it's a plane, right? So again, that's something that we don't want to take for granted. We want to think about sort of actively. So the first thing we want to think about in terms of solving this problem, answering this question, is planes are defined by 2 linearly independent direction vectors. But if I try to get a direction vector for each of these planes, there's no guarantee that, comparing direction vectors from one plane to another will tell me anything about them, because I can have an infinite number of direction vectors parallel to a plane that are pointing in all kinds of different directions. So comparing those vectors from plane 1 to plane 2 isn't going to tell me anything. But there is one thing, one property of a plane that I can compare that will tell me something about that. And it's kind of the thing that we've talked about in the past. That's the most important thing, or the most useful thing about a plane, the most useful property about a plane, and that's the normal vector. If it's maybe a bit strange to think, but if the planes are parallel, then their normals will be parallel, right? In fact, let's see if we can draw that. So I'm just going to draw 2 sort of small planes. There's one, and maybe there's another. Like that, so they kind of overlap. And there's the normal of one and the normal of another, and you can see they would be parallel if the planes are parallel. If the planes are not parallel, they're not going to be parallel. And similarly, if the planes are perpendicular, the normals are going to be perpendicular. The normal of one will be parallel to the other, but again, that doesn't help a lot because you can have infinite direction vectors that are parallel. So it's the fact that the 2 normals are perpendicular to each other that are going to tell me what's happening here, right? So it's a good rule of thumb that when we are talking about planes, we're going to be talking about their normal vectors. So normal vector of the first plane is 2, -3, 8. Second plane is -6, 9, 24. Okay, and now I have to know how to compare these. How do I determine if 2 vectors It doesn't matter if they're normals or not. Now I just need to decide whether these two vectors are parallel or perpendicular or neither. Okay, and we've said this before, how like, okay, I can do the dot product, and if the dot product is 0, then they're perpendicular. But if I already notice that the second normal vector here is a scalar multiple of the first, then why wouldn't I just go to that, right? So I can say 3 times n1 is equal to n2. So when I multiply the first normal by 3 scalar multiplication, I get the second normal, right? And when one is a scalar multiple, whoops, means they're collinear or parallel. All different ways of saying the same thing. Again, that's something really important to get used to, is there's lots of different ways of saying the same thing. Scalar multiple, collinear, parallel, all mean the same thing. Orthogonal, perpendicular, same thing. Yes, we use them in different circumstances, but so therefore, the first vector, the first normal vector, is parallel to the second, but that's not the actual question. So what I actually want to say is, therefore, plane 1 is parallel to plane 2. So I compared their normal vectors, but that's telling me something about the planes, which is what I'm really concerned about. That's what the question was asking, right? And the big lesson here, the big takeaway is, when we're talking about planes, we're talking about their normals. We have to think about their normal. That's going to be the fastest way to compare two planes or more planes together and sort of see what's going on. Okay? Let's try another one. Same thing. This is just asking the same question. Are they parallel, perpendicular, or neither? So I'm going to write out their normals. And, the first thing I'm going to do is I'm going to just, by inspection, I'm going to kind of decide, are they scalar multiples of each other? And you can see that they are not. In the first example, you can see that they are just by looking at it. So that's something that you want to know to look for. And in this one, they're not. Now, I don't have to state this, but I'm going to. It kind of shows my thinking. It shows that that was the first thing I did, because I think it's easy to do. And so why wouldn't you sort of check that first? And this is telling us that plane 1 is not parallel to plane 2. So I don't have to say that unless it turns out that they're neither. I'm saying that for myself. All of this, I'm just sort of showing my thinking, right? And then once I determine that they are not scalar multiples of each other, so they're not parallel, I'm going to look at the dot product. So 2 times 6 plus -3, times -4 plus 8 times 3. And this looks like, I think, 48. Which is not equal to 0. So that means, now if that was 0, dot product 0 means they're perpendicular. If the normals are perpendicular, the planes are perpendicular, right? But they're not. So plane 1 is not perpendicular to plane 2. And in this case, since it's neither, I do have to make sort of all of these statements, right? I have to show why they're not true. So I have to say not a scalar multiple of each other. I have to show that the dot product is not true. And therefore, plane 1 and plane 2 are neither parallel or perpendicular. So this one's kind of the most work, because if it's neither, I have to show that it's neither. I can't. I have to show something. I can't just state that they're neither. Whoops. I have to actually show both. If it's just parallel or just perpendicular, then I can just show that one is true either the dot product of zero or scalar multiple like we did before in part A. And I guess that's a little bit less work. It's a little bit easier. All right, so that's one of the kinds of sort of new questions that we're looking at today. And that's a pretty important one, for what we're doing moving forward, and it highlights the fact that when we're looking at planes, we're looking at their normal and that kind of thing. Like there's a lot coming out of that I think is useful, important ways of thinking about these things. Good mindset to be in for all of this work with lines and planes, right, in 3 space. Okay, example 2, find the angle between planes in B. So these are the same planes as B, is that right? Yep, they are. Now I'm finding the angle between them. Well, the angle between the planes is going to be the same as the angle between the normals, right? So visualize this, and if you want, you can type these out into GeoGebra, and scalar equations of planes is really easy to type in GeoGebra. You would just type that, go into 3D mode, and just type the equation in, and it will know that it's a plane, because it has to be, okay, because you're in 3 space and you're doing a scalar equation. And it's going to show both planes, and you will be able to see that they make an angle with each other. If they're not parallel, if they're perpendicular, the angle is 90. If they're parallel, then they don't have an angle between them. But if they're at an angle to each other, if they're slanted compared to each other, there's an angle between them. It's a little strange because depending on, sort of what parts of the plane you're comparing, you might think the angle can change. So we're sort of looking at the smallest angle between the planes, but really what this question boils down to is what's the angle between the normals? That's the one that we are going to be looking for, and that's how we're going to solve this. So again, we're going to find the normals of each of these. So just hold on, I'm going to write these back out. And now this becomes a question, find the angle between these 2 vectors. That's it. And we did this in Unit 7, right? So it's been a little while, but how did we do this? We used this formula. Cos theta is equal to A dot B over the magnitude of A times the magnitude of B. Right? So we're using the equation of the dot product, the other form, not in Cartesian space, the other form of the equation of the dot product, and sort of rearranging to come up with something that has theta, the angle between them, in it. In this case, my vectors are the 2 normals, right? So what do I need to do to use this equation? Well, I need to come up with the magnitude of each of these vectors. And so again, this goes back to Unit 7. How do we find the magnitude of a vector? We use this formula, and this is in 3 space. So that works out to root 77. So if you're not following this at all, you got to go back to Unit 7 and look at these equations. This is all straight out of Unit 7. Okay, how do we find the magnitude, which is the length of the line? Like we talked about where this equation comes from. This is something that we've already established. I'm not going to go back and reteach it all, but refresh yourself if you need it. But this is a formula, and this is a step-by-step process that we do that will work every time. So it doesn't change. When you're finding the angle between 2 planes or between 2 lines or any 2 vectors, this is how you're going to do it, right? So cos theta. And I'm also going to do the dot product of the 2. Now I happen to already have done it, so I don't really need to rewrite that out, but take a look. We did that up above, right, in the last example, so we already know it's 48. Otherwise, I might have to write that out and actually figure it out over magnitude of normal vector 1, which is 77, times the magnitude of the other normal, which is 61. And then I'm going to do inverse cos of that, right? And I'm just going to do that on my calculator, making sure I'm in degrees. We've talked about this a lot, I know, but holy cow, it's really important. When we're doing calculus, we're doing it in radians. When we're doing vectors, we're doing it in degrees. So when you're punching this stuff into your calculator, you need to make sure that it is in degrees. You need to make sure that you got your brackets in the right spots and your fraction and everything, so that so that it doesn't give you an error and that you get the right answer and all that kind of stuff. Didn't say to round to one decimal place, but I decided to round to one decimal place, and I think it's about 45.5. Okay, so again, we said this originally when we first started talking about planes. Turns out that the normal is so important. And look at almost everything we've done. Every kind of question has come down to comparing those normals. Okay. Okay, last example. I think this is the last example. Example 3, find A. So it's that part of the plane 2. If the planes are going to be parallel, or if the planes are going to be perpendicular. We have done questions similar to this before with just vectors. And again, when you're talking about planes, it just comes down to their normal vector, okay? And so I think I'm just going to dive right into this, and we're going to see what is happening and how you do this by doing it. A, 20, and negative 10. So for them to be parallel, their normals have to be a scalar multiple of each other. And take a look. 8 is negative 2 times negative 4, and 20 is negative 2 times negative 10. So the y and the z components are already scalar multiples of each other. If that wasn't the case, this wouldn't work, okay? Because we're in 3 space, we have 3 coordinates. It has to be true for the first part, okay? But if I want them to be parallel, the easiest thing, yes, we could talk about the cross product, but we've said this before, it's a lot harder. So the easiest thing is to look at scalar multiple. And I'm going to do this. I'm just going to come up with a proportion. It means this has to be true, right? That would mean that they are scalar multiples of each other. It's already true for those two. As I said, if it wasn't true, then I would be in trouble. And so what I'm going to do is I'm going to pick this one, obviously, because that's got the A in it, and I'm going to use it with just one of the other fractions that's complete, and figure out what the A would be that would make them all scalar multiples. So this becomes 8A equals 2 times 20, which is 40. Divide both sides by 8, and I get A equals 5. And you probably could have figured that out by inspection, that I'm doing 2 times 4 to get 8, which means 5 times 4 to get 20 would be what would work. But we have to know how to show our work as well, right? So that's how we're going to show it. I don't want you to just state it by inspection. I would like you to show this process of setting it up for one to be a scalar multiple of the other, okay? And then finally, but I know this is a little bit awkward. It's a bit kind of, we're just kind of forcing it. We're just kind of figuring it out, but that's okay. It shows some really good understanding of the idea of vectors being parallel, scalar multiple, that kind of thing, right? So it's still a good process and good steps to show. The perpendicular one, in my mind, is a little bit more straightforward because it's the one where we're using this property that for the planes to be parallel, the dot product of the normals has to be 0. And I know the normals, so that is going to be 2 times A plus 8 times 20 plus negative 4 times negative 10 will be 0, which means 2A plus 160 plus 40 is 0. So 2A is negative 200. Just solving this simple equation, divide both sides by 2, and A is negative 100. Okay, and done. If A is negative 100, then these two planes are perpendicular. If A is 5, then the two planes are parallel. And it's just this idea of introducing an unknown into one of these equations, setting up some simple equations and solving them. It all comes down to comparing their normals, properties of the planes in general, but looking at their normals. So dot product is 0 to give you perpendicular, scalar multiple to give you parallel, right? Like again, this is all thinking about properties of these planes and what's important, and getting used to the idea of, as I've said before, the notation, but then how we compare them and that sort of thing. Okay, I hope that is okay. That was day 2 of properties of planes, and the worksheet from yesterday, finishing off some of that. And before we move into the second half of this unit, you want to really make sure that you've got that good visual of what a plane is, what's important about it, the different forms of equations that we can have of planes and lines, because now we're going to start to do some other kinds of questions with them. And as long as I kind of have established what's required for lines and planes, and I can think in that 3 space, and I can just think about these objects and visualize them, that's what's going to be the real first step to success in what we're doing next. Okay, so keep that in mind. Hopefully all of that's gone well so far, and we're ready to get into the second half.